can you see my screen?
Yes, sir.
Okay, good. So last week we started the class and I was able to go through what we are going to be looking at for the next 8 weeks. So this week,
Yes.
based on our timetable, we are going to be discussing dielectric properties of solids, and we shall be looking at what dielectric is or what dielectric are. Then we also look at electric field. So let me share my slide. Can you see my slide?
Yes, sir.
Okay, good. So I actually extracted this directly from the course materials which I've sent to you. So if you have checked the course page, you'll have downloaded.
Yes, sir.
Now, the question is, what are dielectrics? Dielectrics are non-conducting materials. So I actually extracted this. Dielectrics are non-conducting materials. Yeah, there is echo somewhere else. There is echo somewhere else. So dielectric are non-conducting materials. So an example is glass. We all know that glasses cannot conduct, and also rubber. That's the reason why they use them. For example, if you put a glove made of rubber in your hand and you touch electric current, you will not feel any electric current in your body. You will not feel it because they are purely dielectric materials and they are non-conducting materials. They don't allow current to flow through them. And they are non-conducting materials. They don't allow current to flow through them. This dielectric depends on Godwin, can you please mute yourself? Godwin, can you please mute yourself? Mute your mic. Cedrica, please mute your mic as well. Okay. So the dielectrics depends on what we know as capacitors. And in physics, in our elementary physics, we can compute what capacitance of a capacitor is using the formula of series and parallel connections. So in this case now, we are looking at the application of these things. So we say that when a dielectric material is inserted between the plate of a capacitor, that is, we have two plates of capacitor, one like this, then you now include in between them a dielectric. Are you getting me now? So at a particular distance between the two plates. So the equation connecting them is what we have in equation 1.1, which is C is equals to K C naught. In this case now, our C naught is the capacitance. So if you don't have dielectric, you have purely the capacitance. But once you have dielectric, there will be reduction in the value and you have C. So the second property there is the dielectric constant K. It has no unit. It is unitless, because if you look at equation number 1, where you have C is equals to K over C naught, C is a capacitance and C naught is also a capacitance. If you want to determine K now, C over C naught, the unit will cancel out. So dielectric has no unit. They are unitless in nature. So if you look at the third properties now, which we call the epsilon naught, which is known as the permittivity of free space, and epsilon, which is the permittivity of dielectric material. So these two things are related, because if you are given the permittivities of the dielectric and also the permittivity of free space, the ratio of these two give you what we know as dielectrics. So the fourth property there is, with the introduction of dielectric material, the energy density becomes this. So if you have a dielectric, which in this case now, if you look at the formula, is coming in with epsilon, because from equation 1.2, you can actually make epsilon to equals to K epsilon naught. If you substitute it inside this equation 1.3 now, you have a dielectric in the equation of energy. Are you with me? So in the presence of dielectrics now, the energy density will become 1/2 epsilon E squared. The E is electric field. So the E in the equation is what? The electric field. Now, when we look at the potential difference between plates now, when a dielectric material is inserted. So in this case now, when you have two plates, each of them like this, then you have a dielectric in between them, it is possible for us to compute the potential difference, that is the change in the voltage across these two plates. So in doing that, you have to take into consideration the potential difference at starting point and the potential difference at the other end, because potential difference is more or less like the moving of a charge from one point what to another. So if you now want to determine the potential difference, now when you have the presence of dielectric, it's going to be V is equal to phi naught over K. In this case, K is the what? The dielectric constant of the material. Am I making sense? So that gives us equation 1.4. Now, there is another concept here that F, the potential difference, is kept unchanged when the dielectric material is inserted. Then we have, so if the potential difference does not change and you have the dielectric in it, so the charge is equal to Q, K times Q naught. So the charge on the capacitor with a fixed potential difference between its plates is increased by what? Factor K. If you look, the reason why we are saying that it's increased by factor K is that if you look at equation 1.5, is directly proportional to each other. The Q is directly proportional to the Q naught, because in this case now the proportionality constant between them is K. It's not an inversely relation, it's a direct proportionality. So automatically, as Q increases, the K also what? Increases by a factor of what? K. So if the charge increases, then the Q naught times K will give us an increase in the charge already, the initial charge. Are we together? So also,
yes, sir.
So also with electric field, if you look at equation 1.6, the same concept holds. That is, E is equals to E naught over what? K. But in this case now, the implication of this, the physical interpretation of this is that if you have dielectric inserted in these two plates, it decreases the electric field because it's an inversely proportionality relationship. It's not a direct relationship. So in the presence of electric, in the presence of dielectric, the electric field what? Decreases. But in the presence of dielectric, the charge increases because it is what? A direct proportionality relationship. Are we together? Godwin, please. Your mic is giving us echo. Just mute yourself, please. Okay, fine, thank you. So that leads us to equation 7. In this case, now we said the net field of electric field within the dielectric is given by, that is, when you look at the total field, the net, what you are going to have, you have two plates now, 1 and 2. Then you insert dielectric in the two plates. You know that the two plates has electric field. Before you introduce electric field, before you introduce dielectric into the two plates, it has electric field. So the electric field in this case is E naught. But by the time you introduce dielectric materials into it, the electric field decreases. So for you to now determine the electric field, the net electric field in it, it is different between the initial one and what? The one induced by dielectrics. And that gives us equation 1.7, which says that E is equal to E naught minus EIND. EIND is an induced electric field because you created that due to the presence of dielectric in the materials. Is it clear? So if you now go to equation, if you combine equation 1.6 and 1.7 together, we define, if you look here now, we have E to equals to this. We also have E to equals to this. If you combine these two equations together, that gives us this. And invariably, we can determine what the induced electric field is, which is equation 1.8. That is, E induced equals to E naught 1 minus 1 over K. So the another properties of interest is the induced electric field in the dielectric is related to the induced charge density, Q induced, through the relationship. If you look at this now, the relationship between them is a direct relationship, but dependent on the permittivities of free space, which is epsilon naught. So the higher the permittivities of the free space in the materials, the lesser the induced electric field. If you look at the relationship between the equation. So the lesser this value, this epsilon naught, the higher the induced electric field. So if you want higher induced electric field, you must have a very low free permittivity of free space. And we know that permittivity of free space is what? A fixed constant. Are you getting me now? I'm just trying to cut this. So what we have just discussed briefly is the concept of what dielectric is all about. Now we are looking at the local electric field. In the previous case, we have been talking about electric field, electric field, electric field. Now, we want to look at what that electric field is. He said it should be noted that every material is made up of very large number of atoms and molecules. So when you have atoms and molecules, there is tendency for electric field to be present because it's a function of charge and electrons. So an atom consists of positively charged nucleus and negatively charged electrons. This we know. So a system consists of two equal and opposite charge. That is, when you have Q, one is negative, the other one is positive, separated by a certain distance. So when you have two charges, Q1 and Q2, but at different polarity, positive and negative. So the distance between them, we call it D. You know, there's in our elementary physics, we call something Coulomb's law. Coulomb's law that tells us that when you have two charges, so the product of these two charges, the product of these two charges divided by the square of the distance between them give you what the Coulomb's force on these two charges is. We know this from elementary physics. So the same thing here, if you now have two charges, Q1 and Q2, separated by a distance, but at different polarity. So how do we compute it? There is tendency for what we call a dipole to be influenced or to be induced in the system. Then the question is, how do we compute this? That leads us to know that when an atom or a molecule of dielectric is placed in an electric field, the positive and negative charge feel opposite forces and are separated from a dipole. So meaning that this presence of this thing can induce a dipole relationship in this system. So now let's try to look at it in details. Suppose that the charges minus Q and plus Q are placed respectively at distance d/2 and minus d/2 from the origin, as shown in figure 1. The magnitude of the potential due to this system at a point S is given by. So now we know that the electric field, the potential difference in elementary physics is Q is equal to V, which is equal to Q all over R. Abi? That is basic definition of it. But now, when you now have two charges at different positions to each other, but in opposite direction, how do you try to bring them together? So in this case now, it's not going to be the what we call the difference between these two distance, R1 and R2. So the difference between them now multiply by divided by the charge in the system will give us the potential. So if you look at this picture now, we have the first charge at minus Q1, minus Q rather, and the second charge plus Q. But they are separated by a distance D. We want to use this idea to derive an equation for dipole in electric field. So if we assume that this point is the middle between the distance from minus Q to positive Q. So this point now, let's call it point O. I'm trying to explain how this geometric concept, we can split it down and derive the equations we are going to look later. So if this point we assume is point O, and we draw a line from here to this point X now. So if you want to determine the dipole now, say where R1 and R2 are the distance of X from Q plus and minus Q respectively. So from this place to this place now is R1. Then from this place now to this place, we have a charge here now. Let us mean that these two charges are depending on what happened at this region. So if the theta is the angle between the axis of the charges and the position vector S, we can write this. I know these equations now, the question is that how did you get this equation and how did you get this equation? So I'm not going to break it down, but I can explain to you. So if you listen very well, you can just pick your pen and try to do the analysis on paper to get it. So let's go together now. Let's say, for example, now we are looking at this distance. I call it point O. So if you extend this distance down a bit up to this point, and you call it point M. So if you draw another line from minus Q to this place, perpendicular to this line that is coming here, you form a right angle triangle. Are you getting me now? So if you call it point M now, so it is easy for you to determine the distance from M to O around this place. Are you getting my point?
Yes, sir.
Okay, so if you are able to determine the distance from here to this place now, so invariably we can say that the distance from X to M now is more or less like the distance from X here to this place. Let's call it A now, approximately, and that gives us this equation 1. No, this 1 over R2, because we are just trying to look for what R2 is. So if you look at this expression now, it's just like adding this to another value down here to give us the total length of this. It is pure geometry. So I expect you to try it. I've done it on the paper here, but I'm not going to show you. Can you see it clearly? Can you see it?
No, sir.
Eh?
No, sir.
You cannot see it?
No, sir. It's not.
It's not
No,
clear.
it's not clear.
Okay, but you can try it.
Okay,
You said what?
Okay, sir.
Just try it. If you cannot get it, I will scan it and send to you, but try it first.
Okay, sir.
Try it first. So that leads us to all these expressions, these two expressions. By the time we substitute them in this equation 1.11, we will get equation 1.12, which is now looking like the potential when you have two charges separated by a distance. So we now say that the dipole moment P now, P is more or less like a product, a vector product of two things. So it's the vector along the axis of the dipole pointing in direction of minus Q to plus Q and having the magnitude. So if you want to determine, it's just multiplying Q times D, the distance, the charge times the distance. So in terms of dipole moment, you can see that equation 1.2 becomes, so we can write this as a in terms of a dipole moment. So if you look at this expression now, we are having P cos theta. When we talk of dipole now, you know, in mathematics, when you want to compute the vector product, are you getting me now? Or you want to find the magnitude of a vector, what you do is that you take the vector itself divided by the magnitude. Abi? You pick the vector itself. What I mean by the vector itself, if you are given, let's say you are given r is equals to 3x plus 2y. So for you to find r squared now, it will be the magnitude of, that is, it will not be the square root of the coefficient of x and y. The coefficient here is 3, that is 3 squared, plus, let's say the coefficient of y is 2, that is 2 squared, that gives us 4. You add them together, you take the square root. Are you getting me now? That gives you the magnitude of the vector.
Yeah.
So it will not be now the vector itself now, which is the expression, which in this case r now, then divided by the magnitude. So that is what we have done here. We look at this, we consider P over 4 pi naught, 4 pi epsilon naught as a constant. Then we now look at cos theta as a kind of a vector relationship. So from this place now, we derive that as P dot R, which is more or less like divided by the r squared, now the magnitude. Is it clear? So look at this expression here. So using the grad of this, you get minus r over this. More or less like what I was trying to explain, but this is a mathematical way of expressing it. So this now turns to this now. Then you now have phi naught, which is the potential of a unit charge. So the field of an electric dipole may also be expressed in the following way. So we can also do it in this way, because we know that electric field itself is a function of the gradient of the charge. The electric field is the gradient of what? The potential. And in this case now, our potential is phi r. So if you take the derivative of that now, you are going to have this expression. Is it clear? I know is it clear?
Just give it a try.
Yes, just
Not
need to,
so clever. We'll give it a try.
yes, better. All these expressions are things you can actually prove. Just try to write one or two things down and see how it looks like. It's a very straightforward thing. But one thing is that your mathematics, your vector analysis idea will be able to help you to explain some of these things. So
Yes.
I think you told me some minutes ago that your battery is not so strong. So
I'm managing it.
you are managing it fine. So I think with what we have just discussed, we'll be able to cover what we are supposed to cover for this week. Because this week, my intention is to discuss dielectric property of solid. So I've discussed what dielectric is and also try to explain what electric field is. So if you look at the notes that I sent to you, you will see in depth of this discussion, which you can read and also pick one or two points. So if you have any question, you can ask me, then we discuss it before we end the class and see what can happen next week. So any questions? The floor is open.
Sir.
Yes.
Wait. So I'm supposed to raise my hands.
Yes.
Are we going to be required to do this proving
in exam?
For this local? Yes.
Well, I cannot say because the point there is that, you know, I might not be the one that will say the question. I might also be the one that will say the question. Because what I understand is that they normally call us to Abuja to sit down and set questions. They will not pick from the pool. I get me. But I would advise you to learn how to prove it. It will help you.
Okay, work on it, sir.
Okay. If you don't work on it and you could not get through, contact me. I will tell you what to do. I've done it already.
Okay, sir. Okay, thank you, sir.
Okay, you're welcome. Another question? Sidikat Godwin, any question for me? Any question? Okay. In the absence of no question, can we call the class a day and we shall do another class for next week? So I will upload the video of this class and also send in the PDF of the lecture.
Good afternoon, sir.
Good afternoon, madam.
Yes, sir.
Yeah.
Yes, sir. I believe just because I didn't join on time, I didn't really understand, but no problem. I will try and check the recording.
I will send in the video.
Follow up.
I will send the video. If you have any problem, you can always get back to me. I'm always available.
All right, sir. Thank you very much, sir.
Godwin, anything?
Godwin, anything? Yes, sir. I would have been have the this thing by hand. We can create time to do that. I would want to say that we are in very busy. We just try to create. So going back to our book now, is going to have this thing. Learning is not a problem. Draw very long time. I've dropped this thing a long time. I just come to it again. So if we have something like just way fast, that electric, I've read that already because
you just need to give it a try. If you have any challenge, you can always get back to me. Send me an email. I will surely respond to you. Any problem you have, just get across to me. I will surely respond. You hear?
Mathematics.
I think you're having issue with your network.
Hello, sir.
Okay, this is a very good suggestion. Yes, you can. You ask if you can create a WhatsApp group. Yes. Create it and add me. There's no problem.
Hear me, sir?
Yeah, you are asking if you can create a WhatsApp group, which is good. Create it and add me. Is that taking Godwin? I cannot hear you. I cannot hear you. You are not audible. You are not audible, Godwin.